Hello and welcome back to the live stream. So last week we implemented the ability to pass structs to and from functions. And the way we implemented that is that the struct object is being passed by pointer. This is because Lauf is a stack-based virtual machine, and the struct object does not necessarily fit on the value stack Lauf uses. So instead we allocate it on the call stack and pass a pointer out. So what this means is when we have a function like forward, which returns a struct object, the actual calling convention for that takes a single argument, which is address where the resulting object should be stored to. And then also for convenience, it then returns that address as well. So what forward does is it then calls the appropriate function and stores it in the stores the result in the pointer that we passed in. And we've already implemented the form from copy elision. So if you can see the make foo function here, which likewise, it takes one hidden parameter for the pointer. And then two extra ones, it constructs a local object result. And then this return result, it essentially does a mem copy, right? We need to copy the result object into the pointer given by the first parameter. But in the case of forward, since the call to make foo is used directly inside the return statement, we don't need to create a temporary to copy the result into, and can just directly pass in the result pointer into the call to make foo. So we've implemented a form of copy elision where we got rid of that extra mem copy there. Now, when we then look at the call for main, so we create our struct foo object right here, temporary on the stack. This happens with one of those local allocations. And then we're calling forward. And what forward is doing is it gets the address of a temporary, passes that as the address to forward. So forward will construct the struct object into the temporary that we've allocated. And then we copy that into our local f variable. And this copy is likewise unnecessary because we directly, right, we can just pass in the address of f directly instead of the address of the temporary, and then we can get rid of this copy. But implementing this requires a bit of a refactor with the way we are generating code for expressions. So I wanted to defer that to this week's stream. So let's talk about this refactor. Currently, we're having in codegen, we're having two functions, generate codegen expression and codegen L value. So codegen expression evaluates an expression and gets its value, while codegen L value evaluates it but results in the address. This is used, so on the left-hand side of the assignment operator, we don't want the value of f, we want the address of f, so we can store something in there. So we call codegen L value for that. And for the right-hand side, we want the actual value, which in this case is also the address, because a struct object is passed by a pointer. But if we had something like int I and then I equals 42, on the left-hand side we get the address of an int, and on the right-hand side we get the actual int. And this is the two modes. But to get the actual optimization of copy elision, we want, I guess, a new kind of mode where we want to evaluate the expression but don't store the result on the vstack, which requires allocating a temporary for the struct object so we can get a pointer to it on the vstack, but directly store it in a provided address. So we essentially having a couple of different modes of variables. So for example, let's say I equals 40f. So I is evaluated using, let's call it L value mode, results in an address on the vstack. 42 is evaluated using store mode, because we immediately want to store it. We don't want to put it on the vstack, because that might require allocating a temporary if it's a struct. So instead we want to directly store it in the address, let's say on top of the vstack. Similarly, f is evaluated using L value mode. So we push the address and then result forward is evaluated using store mode, directly stored in the address on top of the vstack. And what this means for a function call is that we can just take the address of our object and pass that into forward instead of allocating a temporary. And then finally, we have a mode where we actually want the value on the stack. So for example, if we have something like if I, then I is evaluated using value mode, push value onto the vstack. Because to check the condition, we need its value on top of the vstack. And this is then the previous mode that we're using for all expressions. This is the required here. And I guess one last mode is if you have something like here, forward is evaluated using discard mode. Directly don't put anything onto the vstack, right? Since we are not actually using the resulting value. So I think a natural refactoring of our codegen is to pass in, like, take codegen expression and like to define an enum. So enum class expression, yeah, it's called a codegen expression mode, and it contains the four ones. So L value. The expression results in evaluates the expression and results in the address. Not always only applicable for actual L values, right? You can't get you can't assign the number 42 since it doesn't have an address. Then we are having let's say let's call it store. Evaluates the expression and stores it in the address on top of the vstack. Then we are having the value mode, evaluates the expression and puts it on top of the vstack. So this is the value mode, and then finally evaluates the expression and discards its result. It doesn't put anything onto the vstack. Okay, so that's the plan. What this means, codegen expression, and then we take the codegen expression mode. Okay. Let's start by copy pasting U and adjusting U if necessary. So we've got roughly, like, I don't want to do like a visit over all expressions and then we're doing a switch inside of the mode. So it might make sense to group related things together. For example, like null pointer constant and integer constant. They always behave, since they are always resulting in first class types. We can evaluate them by pushing them on the vstack and then calling either store, doing nothing, or popping them again, right? Similarly for type constant expression, for string literal expression, the value again is the address as well, and you can't really store it. So I guess that would be fine as well. I wonder what's the type of a string literal is. I guess it's an array, so that would be fine anyway. Yeah, then we need to. So let's start with those four. Write codegen constant. I guess not just, yeah, codegen constant. Okay. So And these are those expressions. So we can always evaluate them by putting them on top of the tree. First, evaluate the expression and put its value on top of the v-stack. Let's get rid of the first. Okay. And this one calls codegen L value for the string literal, which we no longer want. We want to inline u. Right. So instead we want this logic. Okay. So I guess if the mode is discard, then we don't need to do anything, since they don't have side effects. Okay. And now process the value according to mode. So if it's an L value, and this is only possible if the expression is a string literal, since the others aren't L values, they are never L values, so we can, and it pushed its address earlier, so we don't need to do anything. Zero precondition required. Node has kind zero string literal. Okay. To store it, vstack looks like address value. So we want to call low in store. The builder codegen. We want to get the loaf type of the expression and index 0. So we want to, and of course we have the exact wrong order on the stack. So we need to do a swap. Okay. Value is already on the stack. Do nothing. And discard handled above. Okay. So that's the easy part. Which means that we can, if we're handling a null pointer constant expression, context builder expression mode, integer constant, string literal, and u. Okay. It's a bit annoying that we're doing a type switch here and then we're doing another type switch inside of here, but that's fine. Okay, next up, built-in expression. Right. Those all require special handling. Actually, so built-in expressions, they definitely have side effects, so we cannot elide them on this card. Then when we want to store them, those two produce a result that we can just store. Okay, let's just add a switch and we might refactor it later. So L value. This is, none of those are L values. Built-in expression is not an L value. So we can't evaluate them as an L value. We can store them by doing same thing as we did above. We do a swap And then we're doing a store. And 0 break. Value is already done. And then we need to pop them. Okay. Identifier expression. Right, they always... Currently, an identifier expression always results in an address unconditionally. So... so currently we're always pushing the address of the identifier on the thing because we're having the decay expression somewhere right here, which does the address conversion if necessary. So I think by design, an identifier expression is always in mode value. Okay. So it's always a value, simply the way the ASD is constructed, and it's never used as anything else. Because if it's no, it's either value or an L value. I think it's always used as an L value, right? Because we're unconditionally calling an L value, makes sense. So codegen L value, copy this entire logic over. Okay. Member access expression, same deal. Since we're unconditionally calling codegen L value, it must only be used in the mode where we want to get an L value, and then we've got a decay that takes care of it later on. So we want to get this logic. Right, so we want to get the address of the object, which means we want to codegen the object as an L value because we want the address of it. Right. Okay. Function call expression. Now this is the one why we're doing this entire mess in the first place. So let's try and work through that. So if the function call is, so it cannot be L value, since the result of a function call is never an L value. Unlike in C++ where we could return a reference, which would be an L value, in C there are no references, so the result of a function call is never an L value, so we don't need to worry about that. If you want to discard it, we are in tough luck. We need to, due to the side effects, we need to call it and then pop it. So essentially discard and value are treated the same way, just in discard we're just dropping the value instead of keeping it on the V stack. But if we want to get the address, right, we don't need the result location. Okay, so if we are having a return type that is not first class, we need to give the function a pointer to store the result into. Right, and instead of having the result storage pointer, this is then the case if we will have codegen expression mode store. Right? Then we have an address on top of the V stack anyway, where we want to store the result into. So we don't need to do anything. So let me add a precondition. Precondition mode is not codegen expression mode L value, since structs are never L values. Okay. In the store mode, we've got an address on top of the V stack, and this is the first argument to the call, which makes sense. So this works out, and the function will store that into the thing on top of the V stack. Otherwise, we need to generate space to store the result into. This also makes sense because when we want to get the value or we want to discard it, we are not given a result location, so we need to allocate one. Then we push the regular arguments, then we push the function on top of the vstack. By visiting, we can't visit ourselves recursively using the child visitor because we want to. Okay, so we want to push each argument onto the stack using the. This is a bit ugly. Not just a bit ugly, this is a lot ugly, but let's just do it that way. So we want to get the value. And for the address, we want the L value. Okay. Oh, no, I can't do that because then I need to save it. So let's generate an actual recursive core. So it currently does visit tree, which auto visits side expression. So let's say, let's get rid of that and manually visit the children. Okay, right. So we need to then recursively visit our children ourselves. So in this case, we want to visit the argument as a value. Get the value of the argument. So codegen expression, context, builder, expression. My language was a bit dead. Okay, it's too many compiler errors. Okay, so let's. Right. Okay, let's remember to change that later, just so I can get autocomplete in the meantime. So we want to codegen the expression using the builder, the underlying argument, and we want to get its value. Okay. Identify expressions not recursively. Right, and then here we're manually visiting the members anyway. So here, but instead of using the child visitor, we use a recursive call, context builder argument, and we want the value. Context builder function, and we will want to get its address in order to call the function. And we want a function pointer. So cast expression. Get the value of the thing we are casting. Context builder expression child. Codegen expression mode value. And right. So if it's void, we are getting the value and then we're discarding it, and we can now optimize that to say if we're casting it to void, then we want to codegen expression mode discard. Otherwise, right? And this is a potential optimizations if we have functions like, for example, we don't need to build a string literal if we're casting it to void. So now the expression knows how to discard itself best. Value has been discarded already. Yeah. Okay. Why is that a repeated branch? Oh. Yeah, that's annoying. Hide this lint. Okay. Then this logic should all behave the same. Decay expression. So decay expression. This is interesting. So currently, a decay expression unconditionally evaluates the operand as an L value, and then we're loading it if necessary. This is why identifier expression always generated the address, because the decay expression took care of the load. And now we could refactor that, but let's do it not for now, and like if it works, then we can refactor it further. So for now, we unconditionally evaluate you as an L value, and then we do the load later on, but we can clean that up. Okay, to do evaluate as value instead. So unary expression, we want to get the value, expression child value, and then we process it, right? And here we want it, because this is, this is the increment operators, they need the address, so we evaluate again, but this time as an L value. And similarly here, and similarly, again, this can be refactored, because now we're having smarter logic. Get an expression out. L value. Okay. Arithmetic expression. We evaluate both sides and we want to get its value. Left and right. Similarly, to compare things, and okay, sequenced, right? This one is like logical AND and logical OR, where we're doing potentially evaluate them, but in other case we want to evaluate them as a value. So context builder left value, similar thing for logical OR, and logical AND, and then finally comma. And I think I'm also pretty sure that in C, the comma operator is never an L value either, unlike in C++, so we don't need to worry about it here. Okay, assignment is now a bit interesting. So we're first pushing the value that we're assigning. Again, so currently we're getting the address unconditionally and then we're loading it, and we can do that smarter as well. So this can get another refactor. So do what the comment says and get the address. And then get the value of the right-hand side. So this logic here is for the compound assignment, where we need both the value of the left-hand side as well. Then we do the operation after we're getting the value on the right-hand side. So here we definitely want the value. And similarly here. Okay. The stack now contains the value we are assigning. Right. Right. So currently we're getting the value, then we're getting the address, and then we're storing. But this entire thing can be, so we first get the address, right? This was the entire point. So get the resulting address. get the address of the left hand side. Right. So codegen expression mode L value. In this case, we manually need to store it, but that's okay. Manually store result. Actually, no. Right. Because we can... No, in this case, we manually need to, never mind, store the result by getting the... we already having this up. Okay. But in this case, we can just say codegen expression mode store, right? And this will evaluate the right-hand side and directly put it into the address that we put on top of the stack. Which also means that for all those expressions, we forgot to handle the expression mode, where we essentially need to do this entire logic right here. After we evaluate the expression, we might need to store it. Right. So let's extract u into a function. Void codegen. No, let's not make it a function. Let's make it a lambda. Process mode primitive first class. Which is this logic here. Expression is not an L value. We already pushed the value on top of the B stack. So do nothing. Okay. And now after built-in expressions, we can just store it if necessary. Where was it? Right here. Process mode, because the result is a first class type. Similarly for all the like cast expressions, actually like the entire branch thing, right here. So first class means that we can call store and don't need to call memcopy, but we can actually just implement it. Right here. So if it's a first class type, we can call it store. Otherwise, we need to call memcopy. And we maybe already removed that. There was something I can copy paste over here in assignment. I've already got rid of it. Okay. So we want to call memcopy. Call built-in b love lib memory copy. And this is destination, source, and count. So push the destination. So essentially, it's again the wrong way around. And then the size. Codegen layout of the type size. Okay. The V stack looks like this. Address value. Need to store value in address. Value is actually a pointer to the thing, to the object, since it's not first class here. Okay. And that should take care of this logic. So we just need to, instead of doing the store inside the assignment, we are doing the store after every instruction. So process, let's not call it like store. Yeah, I don't like the name, but it's fine. So process mode. Okay. Call the function cast expression. So the function, we might need to process the mode as well, but differently, because we did the optimization. Essentially, all we need to do is if it's discard, then we need to discard it. And it in this case is the pointer. Okay. Process mode. Process the mode. We're doing that here. We're doing that here. We're doing that here. We're doing that here. Then we store the result. So in assignment, we get the L value. We're calling store, and because we're calling process mode everywhere, this will now actually store the thing, which we might need a mem copy, but if we are calling a function, then we can get the optimization that we are after. Like, what's the result of the assignment expression? Right, this is since we are leaving the address on top of, since the result of assignment is the address left side as an L value, we duplicate it. So we duplicate the top value, and then we might need to do another store if we're having a nested assignment. Okay, conditional expression. Right, so we want to evaluate the condition. So we want to get the value of the condition. Context builder, codegen expression mode value. Then we want to get the if true case, and we want to evaluate it in the same way that we want to get our own expression, right? So it just forwards to. Okay, so now we don't need this one. We also don't need, yeah, copy pasted that entire thing over. And I wanted to don't visit any children at this point. Okay. So now we just need to fix the calls. So codegen expression, we want to get the result of an expression that we want to store in the native global. Aha, look at that. This means that we want to push the address and call codegen expression mode store. And this will now do the store for us. Right here, we want to get the, we're doing a store, right? So we codegen expression as a store, and the address is apparently, right, address is on top of the stack. So we can just call store and have the expression take care of the store for us. What the hell are you doing? Oh, right, this is string literal stuff that we don't need to worry about. None of this calls expression, so it should be fine. Return statement. Right, so we want to generate code for the return expression, storing it in the return pointer. So what's the return pointer? It's a local that contains the result value, so we need to load it. Local address, so we get the address of the thing that stores the return pointer, and then we load it. Load field of the primitive type, and then we say codegen expression, and please store that into the pointer that we put on top of the stack, and this should get rid of the mem copy. Right. This now generates a mem copy, which we never need to do, since we always put it on top of the Like we're always putting something on top of the... Okay. So we don't need to generate the mem copy. That's true. What we need to have, need to have a case distinction. So if the return pointer is null, return first class type by evaluating it, the expression, as a value. Context being statement expression, codegen expression mode value, right? So since we, like if it's first class, we are returning by putting it on top of the B stack, and then, so we want to get the value, else storing it in the return pointer. And then we want to, like, the result of the call is the return as well. So first load the return pointer, duplicate it, since that's the value we are returning. And then we're doing the store. Store it in the return pointer. And then we can do an actual return. Now, when we do a codegen expression mode, yes, this will consume the value, so we have to duplicate it here. Okay. We are almost done. But we're just having the thing like we evaluate the condition by right. So for example, also the expression statement. Like something is visiting, right, here we're visiting expressions. And we don't want to visit expressions because we don't know anything about the mode. So we need to, let's put in a seal of unreachable. Need to manually visit expressions. So we can provide the appropriate mode. Which means that, for example, here we rely on the implicit visit. So evaluate and discard the expression. Because an expression statement is something like that, right? We evaluate foo and then we discard it. So codegen expression, context, builder, statement, expression, codegen expression mode, discard. And we don't want to automatically visit the children. Okay. Similarly, here for the if statement, we want to evaluate the condition as a value. Right? Since we want the value of the condition. Context, builder, statement, condition. Codegen is as a value. And similarly, evaluate the condition in loop header as a value. Context, builder, statement, codegen, expression mode. And evaluate you as a value. And that should be all. Now let's see how much code we broke. Okay. Essentially everything. So what's the, like, some pretty simple stuff is probably going to break. Let me build, let's see, struct. Let's see. So just start with a very simple example. Int main. Do you still work? You do still work. Okay. Ceilo print 0. Right. So invalid stack index. We are popping something that was already popped properly. Right here. So discard. apparently we've discarded it already. Right, since none of those print. Okay, this can be easily fixed. So in free, we get a value on top of the stack, likewise in heap alloc. But in assert and print, those expressions always evaluate in void, so we don't have a value to discard anyway. So hang on. So what about process mode? If the type of the expression is void, then assert. Because if you have void, the only thing you can do anyway is discard it. What else would you do with void? And then we don't need to do anything. Nothing is put on top of the V stack for void, right? Because what would we put there? Right. Okay. A lot better. Array and assignment stuff fails. Let's tackle assignment first. Right. Hang on. So we're probably the result of the assignment expression is the result of assignment not an L value. Is that only a C++ thing? We'll check the compiler. Now the AST is somewhere we're having an is L value function. Yeah, assignment is not an L value. So we don't want to evaluate the result of assignment. So we're not getting the number 0, we're getting the address of I, which is by the assertion fails here. So when we're assigning the assignment expression, like I'm also pretty sure. Okay, like we are evaluating the expression a lot, too many times if it has side effects. So this logic is broken in multiple ways. Okay. Since the result of assignment is the value of the left-hand side, side B needed again. That's how do we best structure that? So this leaves the address on top of the stack, but then the address is considered to be the value right here. Right? But instead we need to then do another load if necessary. Man, that's a bit annoying. Like, is that really what the standard says? That the result of assignment has the value of the left or pointer, but is not an L value. Huh. Like it is in C++. Okay. So we want to evaluate the expression once to get its address. Then we want to get the value, right? So we want to get its thing, and then we want to get its value. Right. I think it's easier if we do switch over the mode here. And then refactor it later on. So this is unreachable. Result of assignment is not an L value. right? And then in store, what we need to do is get address of left, get value we are assigning into as store, right? And this will then store the address of the left-hand side. And then we want to get the value that resulted in the assignment. We also want to store it in the address that's like our resulting expression is now that value. We also want to store that again into the other thing. So let's say like this is a bit dumb, but like how often do you like have nested assignments? So it's probably fine. So get the value we're assigning into as a store. Evaluate value we're assigning into as a store. And then so duplicate address, evaluate value we're assigning as a store, load, and then yeah, we can just do mem copy address into address on top of the vstack. Here we want to get address of left, duplicate address, evaluate value we're assigning into a store, load value, and to discard, we want to get address of left, evaluate value we are assigning into a store, and then we're done since we don't want to get any value after all. This is the common case. So what this means is that we actually like if you look at this tree, we're using the assignment expression as an L value. For everything else, we're using, like, we need to introduce a decay expression right here. Since we want to usually, oh no, because it's not an L value. Never mind. Okay, so let's add a precondition that code mode is not L value. Okay. Then in either case, we want to get the address of the left-hand side. We know how to do that. Yeah, let's also duplicate it unconditionally. We might need it again. Then we want to evaluate the address that we are assigning into as a store, which is this logic. And for that, we load from the address, load the value of the left-hand side, load the right-hand side, evaluate the right-hand side, and combine the two, manually store the result. And this one does evaluate the right-hand side and store it into the address on top of the vstack. Okay. And now we want to, depending on the mode. Okay. So this one is unreachable. Precondition failure, let's say. Okay. Here we want to mem copy vstack, right. Vstack looks as follows. Store address, left address. Mem copy, store address, left address into store address. Since we want to store the value that is the result of the assignment into the left-hand side. So call built-in let memory copy. And this is again destination source. Hey, this time it's actually the correct order for once. Inst uint builder codegen layout that many bytes. We have the left address on top of the vstack loaded if it's a first class type. Codegen love type expression type load type 0. And here we're having the thing on top of the vstack, and we want to discard it. Okay, now the assertion passes because, and the stack is a bit messy. So we're getting the address of I. We're duplicating it. We are pushing 0. We're doing a swap. We're doing a pop. We're storing 0 into the thing. We're doing another pop. We're loading the value again. Oh, man, the stack is messy. Then we're pushing 0 and comparing it and doing the assertion. Yeah. Like, this isn't ideal, but okay. What do the tests say? Okay, we've got an invalid address in assignment. Okay. Let me guess, compound. Yep, compound. So line 5. We're getting the address, we are duplicating it, we are getting its value, we're pushing 0, we're doing the addition. We are storing whatever that is into the address on top of the vstack, which is the address of 0, which is big enough. So why are we getting an invalid address in line 5? That's a bit odd. So local address gets duplicated. Then we get the value, we push 2, we do an addition. Oh, we need yet another swap. So right here, manually store the result. Right here. Okay, so now we are getting to the part where we're having okay, assertion failures in codegen.cpp line 447. That's a bit okay. So what are we doing? We are evaluating. Ah, right. So it is an L value. Right. Probably we're taking the like address of or something. So it might be a value. What happens if you just do nothing? Progress. Okay. value, or like I'm not quite convinced that this is correct, but let's move on. Global.c. Right, so we want to evaluate an identifier at this point as a value, probably, yeah, in a unary expression. Okay. Wait, that shouldn't happen. Because this should then be like used with together with a decay expression. Identifier expression decay, identifier expression decay. Identifier expression pre-increment no decay. Oh right, because we want. Right, so this logic is correct. The pre-increment one is broken. So where do we have unary expression? Pre-increment. Like then, oh right, because it's an L value. So and here we need to get the value. Here we want, like, we are evaluating the expression twice anyway, though it is broken if the expression itself has side expects. So get the address on top of the v stack. And then we duplicate that. And then we save a copy into the L value, which requires some sort of swap. So vstack looks like this: address, new value. We want that the new value is left on the stack, so we want to first duplicate it. First duplicate new value, as that is the result. Which means address, new value, and then we want to get the address, move the address on top of the vstack. Uh-huh, 0, 1, 2. Okay. And then we can do a store operation. And similarly here we want to first get the address on top of the vstack. Then we do allow to get the value. We duplicate the out value, right? At this point, so the vstack looks like this. So we've got the address, we've got the old value, and we've got the new value. Store new value into address, which means that we need to get the address over and store it. Okay. Okay, now we're just having a couple of edge cases. All right, here we don't want to pop. Evaluate it as an address. And similarly here for dref. Because ironically, dref doesn't actually result in the value, it results in the address, since we want to use it as an L value. And then we've got a different load. So let's add a deref, let's add a precondition. Codegen expression mode L value. The result of deref is always an L value and decayed if necessary. Perfect. Okay. Almost there. Heap.c. Probably something to do with the built-ins right here. Right. So if the function auto function requires return pointer, this one function requires return pointer. So if the function requires return pointer, we have the return pointer again on top of the v stack and need to discard it. Okay, so now only void is crashing. Which is probably because we're having a null pointer here, yep. Wait. A statement is a return statement, but you don't have... Oh, right, because this one is optional. Right, because a return statement, like this one, doesn't necessarily have an expression. So if not statement expression, do nothing to evaluate the expression, since there is none. Right, and this one is a bit broken. I guess. What? Oh, this one actually returns like a different kind of point. Right. How do I know? Check whether you have a thing. Like I guess like so. I think that should work. Yep. Which means that all of the tests now pass. Finally. That took a while. Okay. And I can try that example again. Okay. That one has a bug because none of the tests currently use structs. Right, so we want to store it in the return pointer. Right. And no. That's interesting. So, like, the current block has two things, but forward only is supposed to return one, right? So why do we have two things? Probably a codegen expression, like we're duplicating it here, but I'm pretty sure we need to, because store in general doesn't leave things on top of the stack, right? Like, store consumes it. Right. Because if this is mode store discard, then we're not discarding it. Hey, and that one works. Okay. Let's get the stack. Like, it doesn't do the correct thing, but at least it compiles. Right? This isn't the correct values. So let's say make foo 11a. Okay. Still not the correct values. So let's see. Make foo. Like, we still get the local address. We're doing a store of 0. We're getting the first thing, we're dereferencing it, and we're storing a U8. No, wait, this is fine. Just a bit confusing to read. Let's make you an int as well. Then we should have more, make it a bit compactor to read. So 10.5, right. This one sets A to A. Let's see if it's correct here. Result.A, result.B. Right, so this part is correct, 11 and 97. Okay. So the issue is entirely in the return, which shouldn't be too surprising since that's what we've changed. So return is line 14. So we're getting the return address, we're duplicating it, we're getting the address of the result variable. We are swapping the two, so we can call memcopy, and then we copy 16 bytes over. Right. That part is correct. Over at main in line 26, we are getting the address of our local object foo, right? We are duplicating it. We are pushing 11 and 97. We're calling make foo, which should store it into that address. And then we have a bunch of pops. So why are we not... And then we're calling, like, loading the first 8 bytes and printing them, but they're zeros. So why are they the zeros? Like, ideally, like, this is the calls, and like the call set, this looks what we want, right? There's no memcopy here because we're just calling make foo and passing it directly the address where we want the stuff to be stored. So we fully elided all copies here. Like, this part looks correct, but then we are getting, so we are storing the value that's on top of the stack in 0, then 1, 2, right. So this this local allocation stores the resulting value. And when we're calling memcopy, we are getting the pointer stored in here. Hang on. So this pushes, so that's vstack. So vstack. We're loading the return pointer onto the vstack. we're duplicating the return pointer. We're getting the local address of 3, which is our struct result address. We're doing a swap. We're doing a swap and then we're doing a copy. So what we're copying is we're copying the f object into result and not the result object into f. So somewhere in return statement, right here, we are, oh, this is not actually done in return statement. So who swaps here? So in return statement, we can see the this is the load local value. Then this pick 0 is this pick 0. And then we're calling codegen expression right here, where we're having a bogus store. And the expression is identifier expression. Right, because result is an identifier expression. So identifier expression. No, this is not identifier expression, this is decay expression. Function make foo, decay expression, identifier expression. So decay expression. Decay expression evaluates the child as an L value and then loads it if necessary. It is not a first class type, so it does not do a load of the child. Instead, it just does a process mode, and the process mode looks like this: address and value. Oh, right. We don't need a swap here because the destination, like, value is the source. Okay. Right. So now that one works. And we should be able to just call forward. And it still works. And we just have a single, like, no mem copy in main, because we're just passing the correct address in. No mem copy in forward, because we're just passing the correct address in. Just a single mem copy here in make foo, because we're having a local at a different address than the return value. Which took a lot longer than I anticipated, but that's a great optimization. So this is C++ 17 guaranteed copy elision implemented in C. Let's commit that. Implement more copy elision. And this required a refactor of expression evaluation. Okay, now there are still a couple of to-dos. That one's fine. Here, for example, the decay expression. So what we're currently doing is we're evaluating it as an L value, and then we're loading it if necessary. However, we can just ask the thing to evaluate it as a value instead. So, we can just ask the child to evaluate you as a value. And then it will do the load for us, if it's possible to do the thing. Okay. So what this means is that we're having a couple of things where we are currently asserting here we are asserting that it is an L value. Instead, we evaluate the expression as an L value, and then we want to load it if necessary. So first of all, let's move you into a separate function. Write codegen identifier as L value. So let's that. Okay. Codegen identifiers L value. And now we need to do different things depending on mode. So codegen as an L value. Codegen is an L value and then we're done. To get a store operation, we get the address and then we can just memcopy it over. Memory copy, which also needs the number of bytes. Okay, so we get the address and then we just copy those bytes over. To get it as a value, we need the actual store, the actual load. Codegen load type. Load field type 0 after we got the address. And to discard it, we don't actually need to do anything. No need to evaluate anything. Okay. And similarly, logic for members. So we have add another function codegen member as an L value, which requires a recursive call. So let's make that possible. And then we can use you. Pretty sure it's just the same deal. We're just codegen member. Member as L value. Member as L value. This evaluate and discard the object part of the expression. Codegen expression. Since the actual member access like that's a no up. Okay. Right here, so a function call. Okay. Let's just see what breaks. Right. 840. The result of a deref is already right. Right. So deref might need to similar logic. We evaluate it as an L value and then we deref it if necessary. And now here's the interesting thing is, so we need to pass in a new argument because like if it's like this is incorrect, this one. So previously when we having like we expecting L value and then the L value was already on top of the stack, but now we might need to load it. So like I think we need to give you an argument and say whether the on top of the stack is an L value or an R value. So let's say bool top is L value, right? So CLOP precondition top is L value because otherwise it is already an L value no need to do anything. Okay, but in this case, if it's an L value, then we need to load it. Load field b type 0. Okay. Otherwise it's already on top of the stack, right? And this one now makes a lot more sense. We just need to, right? So you are never an L value, right here. Result of the cast is never an L value. Result of decay is by definition never an L value. Actually, instead of always loading it as an L value, we can do just forward it and load it as whatever is necessary. And then we add another precondition that the result of decay can never be an L value. So we do that. Okay. And here, the top of the stack is an L value if it's deref or address, otherwise it isn't value. So essentially that. I can repurpose that logic because that one returns true for. Oh, right, address off. It's interesting. While address off, so subtle difference here. So deref, we get evaluated as an L value, which pushes the address. And then the result is logically also an L value. So when we want to get the value of a deref of operation, we need another load operation. But when we get address off, we're also evaluating it as an L value to get the address. But in this case, the address itself is the value. So we only want to do the load for deref of the address to value conversion, because then the address is not the actual value of itself. So yeah, C is a bit confusing. Process mode. Arithmetic expression, never an L value. Comparison, never an L value. Sequenced, never an L value. And now we're getting a bunch of assertion failures. Okay, interesting. So let's do that trick again. The top is not an L value. Yes. Oh. Interesting. So in this case, like we're doing an array index operation, which is an arithmetic expression, but the resulting thing is an L value. Because, right. Because like we're doing a pointer offset, which is an L value. Because it's a pointer, and like, wait, no, it's not an L value. Oh. But where are you called? There are many caustics here, so right. So we want to deref, right? Deref evaluates it as an L value, so we get the address. But the thing that we are evaluating, like, is an arithmetic operation, which I guess isn't really. I mean, yes, it is an L value. So this is an L value. Okay. So the top of the stack is an L value at this point, but we don't want to load it. So what's the issue with the precondition? So we have an address on top of the stack, and we want to load it as an L value, so we want to keep it as an address. So we don't need to do anything. Right, and this also then... Why is the decay expression used as an L value? Because we want to dereference it, so we're dereferencing a decay expression. Right. So I guess that assertion is also just broken. No, 756. And now we're getting assertion failure in pointer.c. Line 6. So that one is broken. So we're having an assignment, the expression which takes a pointer and assigns it, and here we're having a pointer, we're decaying it to get the value, and then we're getting dereferencing it. And the result is 2, right? So we're printing, what we are getting here is the address of the thing, of the pointer. So something about the decay logic is broken. So the dereference operation of the pointer should get its value and then load it. Wait, but why is the decay expression used as an L value? That doesn't make any sense. Like, this shouldn't be used as an L value. And so we get the... so we've got the def operation of a decay thing. So we're doing a def operation of a decay. That is interesting. Right, so we're having star pointer on the left hand side. So what we want is we want to identifier, decay to get value of identifier, and then we want to deref that. Right. So we want to codegen the expression as an address, but the thing is a decay expression, right? So a decay expression, if it's being passed L value, if a decay expression is used as an L value, codegent as an L value, then what this means is that we want to get an address. But in this case of the decay expression, it is not it is not the address of the expression itself, but instead just the value of the thing. So I guess it makes sense to rename you address. So we want to get end results in the address, which is only applicable for actual L values or expressions of pointer type, because they will also result in an address. Or the entire thing with decay. Yeah, okay. Like it's not ideal. I think we can actually start to get rid of decay in that sense. Like, don't need to evaluate it, make it part of the AST anymore, because we've got the actual logic now somewhere else. But this is not a refactor. I'm going to take it. Okay. Optimize codegen for decay expressions. Okay, so the stream was long and a bit complicated, and we didn't get to, like, what we did was quite cool, like with the copy elision, but we absolutely did not get to new actual compiler features. Sorry about that. I thought it was easy. Famous last work. So thanks for everybody who stopped by. And next week we will take a struct initializer and like maybe go to unions or type defs and some like more front-end stuff instead of all this backend wrangling with the stack. Thanks.